Have you ever considered how your favorite songs would sound if played on a different planet? Or if the sound of cars and aircraft would be unfamiliar? Maybe even the howl of the wind would feel alien. These questions invite us to rethink something as familiar as sound when placed in an alien atmosphere. Our presentation, Simulating Acoustic Wave Propagation on Mars, seeks to examine this behavior through computational simulation. My name is Hayden Baird. I'm a current PhD student and researcher at Utah State University. My advisor for my degree and research is Dr. Charlie Zane. This research was partially funded by the Utah NASA Space Grant Consortium with computing resources provided by the University of Utah Center for High Performance Computing. How sound moves in different environments can be fascinating to consider. Those who scuba dive are familiar with the high-pitched, tinny sound from hitting an air tank underwater when trying to get another diver's attention. When considering how sound moves on another planet, the unique environment should be the first step to setting up the problem. What we're using here is a realistic piece of Martian terrain data, and we're trying to simulate a acoustic source, in this case, a aerial vehicle that is already on Mars. The Martian atmosphere is drastically different than that of Earth. For example, the background pressure is less than 1% what we find on Earth. The temperature varies quite drastically between the two as well, with higher variance throughout the day experienced on Mars than we experience here on Earth. This relates to a very significant change in the speed of sound experienced on Mars compared to Earth's atmosphere. The Martian terrain is also very different due to lower gravity and no tectonic activity. This creates different terrain properties that we implement into a high-fidelity acoustic simulation. With the environment details defined, what can we learn from simulation? This animation illustrates acoustic pressure pulses generated by a moving source represented by this pink square. This source represents some kind of a UAV or helicopter as it traverses over a set of terrain. This terrain data was taken from a real scan of the Martian terrain. These blue diamonds here represent virtual microphones to pick up acoustic pulses. What we can see from these pressure pulses is accurate reflections and diffractions around complex geometry. So what kind of signal does one of these microphones pick up? These figures represent the signal recorded by a receiver at an identical location in the terrain, with the only difference being the atmospheres being simulated. What we see between the two signals is a similar overall frequency profile, with the only difference being the Martian frequencies being shifted leftward to lower frequencies. This shift can be quantified based off of the ratio of the speeds of sound. The speed of sound on Mars being around 243 meters per second, and the speed of sound on Earth being roughly 340 meters per second. This results in a shift in the overall frequencies, where if you say have a 100 hertz frequency on Earth, you'd get around a 71 hertz frequency on Mars, or 71% of the same frequency. So what would we hear if we were actually there? These spectrograms will give us a visual representation of frequencies recorded that we can also audibly hear. Let's hear what a receiver in an Earth atmosphere recorded. What does that same receiver sound like on Mars? We can audibly hear distinctions between the two atmospheres, with Mars having low, bassier frequencies compared to that of Earth. The general frequency profiles are similar overall, with the Martian frequencies again being squished down to the lower frequencies. These spectrograms also allow us to see when the source is nearest to the receiver based off of this strong pulse in both simulations. This happens between 2 and 3 seconds for when the source passes over. We can also see some distinct frequency shifts over time with different reflections interacting with this receiver. In conclusion, using acoustic simulation, we're able to find acoustic signal changes based on terrain interactions, in this instance, interactions with the Martian terrain. Atmospheric effects tend to shift peak frequencies based on a variance in speed of sound and background pressure for Earth and Mars. Terrain and atmospheric properties for our simulations are heavily based on previous research measurements. This research provides a critical stepping stone for future planetary research, such as weather measurement and future research mission design. Thank you.
Thank you for that presentation, Hayden. If you and Charlie would like to come off camera or on camera to answer some questions, I'll go ahead and spotlight you. Right. And then, well,
Hello.
alrighty.
All right. Yeah. Thank you so much, Charlie and Hayden. Now you got me wondering what my favorite song will sound like on Mars. And I just got my Spotify wrap up this today, so I know I'm extra curious. But we do have some questions in the Q&A for you. Uh, First one is from Avery, and Avery is asking, how might these results be used in future research?
So we want to use these results primarily for, sorry, me and Dr. Zane are in the same room, so I'm going to get some feedback in my ears. But for future research, we want to add weather effects into our simulations to see how that changes the acoustic signal based off of receiver location. This also goes into the next question that I see, where we hope to be able to set a array of receivers to back propagate the weather data, or to be able to record distant weather events to see what they sound like from a distance, for say on Mars, find a dust storm miles away and close down sensitive systems before that dust storm even comes close to the rover, especially with the communication delays between our rovers on Mars, on Earth, and being able to make those decisions in real time.
Yeah, and thanks for,
Yeah.
oh, go ahead, Charlie, please.
No, I just want to add that the acoustic measurement is another effective way to measure signals on other planets. And this work is beginning to explore that possibility. And it seems it's a promising technology that we can use on Mars and probably other planets to measure the weather and to measure some propagation properties. Go ahead.
Oh, yeah, thanks.
Yeah.
Sorry, I was stuck on mute there for a second. And just for the benefits of our recording, you also answered our second question here, which was, this work can help with Martian weather research and future missions, and you elaborated on that. So thank you so much. Maya is asking in our Q&A, was there anything surprising about your findings?
For us, the findings correlated pretty heavily with the atmospheric conditions we were putting on there. So in terms of surprising, what we were more surprised about is the amount of data we had to set up the simulation rather than the results. The results are going to need some more investigation, especially when putting on temperature and weather effects. That will create some stark differences between Earth and Mars specifically. But the sound signals, they're going to propagate relatively similarly, with some exceptions, with some atmospheric differences that you need to take into account with simulations, specifically with the gas content on Mars being CO2. It's prone to attenuate certain frequencies and damp them out a lot quicker at longer distances. So.
Yeah, I want to add that we also find that the Martian terrain structures created some interesting acoustic destruction patterns, although we didn't show it in the video. But but in the presentation this morning, Hayden presented some interesting results due to the Martian terrain destruction patterns that influences the acoustic propagation. So if you say any surprise, probably this is one of them. It's not really surprising, but it's just showing that how complicated this Martian terrain can influence acoustic propagation.
Thank you so much. And that kind of leads us to our next question is, this one's from Anashay, is why are we interested in acoustic signals on Mars to begin with?
So what got us interested in this was there's a lot of research about Martian acoustics and what we expect, but recently, specifically for the Perseverance rover, there is some acoustic data that we were able to get that had some unexpected content in there where part of the Perseverance mission was the Ingenuity helicopter. And they expected to not be able to hear it past a certain distance, but they had certain frequencies actually be able to record it at distances of around 100 meters, which was wildly unexpected. Mars is a really good candidate for us because it has an ideal gas atmosphere and it's a close neighbor. So we can get some really good difficult to actually go and research due to needing to send an expensive rocket there. So,
okay. And I just want to add, if I may, we touched a little bit that acoustic signal we can back out the Martian environment parameters by using acoustic measurement. This is also because some of the other measurements, as you know, that the Martian environment is a very harsh environment to any equipment, and we seems to be able to make the acoustic measurement equipment more sustainable under Martian environment. Therefore, they can provide more information about the Martian environment, probably than some other means of measurement.
Oh, all right. Thank you so much. Let's see. Our next question is how important are the differences between Earth and Martian terrain to analyzing these acoustic signals?
so the terrain differences that we were primarily looking at was the porosity of the terrain. So the ability for sound to permeate into the terrain, get absorbed and diffracted, and move through it. In terms of the reflection patterns, they're very similar, but the amplitude is different. So we used like a sandy terrain for our simulations. So you can imagine like clapping in a desert versus clapping like a slot canyon, very rocky. The sound gets partially absorbed by the sand rather than in the rocky canyon. It'll echo around quite a bit. So that terrain is important in adding that extra layer of potential damping coming from the absorption of the sound into the terrain itself.
And the effect of the shape of terrain probably is very significant. I just want to add that.